Well, good afternoon, everybody. I'm Professor Marco Beiersbergen, and here next to me is Professor Konrad Schoon. And we want to inform you about the high-tech innovation specialization in the master here in the Leiden Science Department. Yeah, I said before, questions, reactions are welcome, but please put them in the chat and then we can address them later. So what is the high-tech innovation specialization? It is a specialization for master students in one of the science topics that are doing a master in one of these science topics. And the focus is on the intention is not only to focus on the topic itself, but also to bring interdisciplinary activities in there and to focus on technology and research also in an industrial setting. The program is related to and important for the high technology sector, and then you should think of semiconductor, nanofabrication, scientific instrumentation, but there is a lot more areas where this program would be relevant for. The high-tech innovation specialization is on top of, or maybe not on top, but it is a part of a normal topic in astronomy, in physics, in computer science, in mathematics, and in chemistry. So in addition, and I wrote here physics because I'm from the physics department, but it is true for the other ones as well. The idea is that in addition to the topic that you're studying, that you're also learning more about design, development of new technologies, instrumentation, and systems in a more industrial setting. So the idea is to combine high quality research in the field of the study where you're doing your master with gaining experience in a scientific business or industrial science environment. So what we want to offer you is a learning from professionals that are operating in this field, but also by doing internships, gaining first-hand experience on what it means if you want to develop new technology and based on research, bring that all the way to applications and to society. To give you a few examples, in scientific instrumentation, for example, you can think of space instrumentation. That's a field in which I am active and where there's a lot of technology development and also a lot of research being done in order to develop new technology, but that you then also have to bring to real instruments that have to be built, that you have to work together with industry, where industry will pick up part of the research and where in the end a product has to come out. And in the case of space, this is usually not in large quantities, but there's a lot of research going on to build new things. But also, for example, in large science programs, such as the Einstein telescope, there's a lot of technology development, there's research done at the universities, and there's research done together with companies, with industries, with institutes in international consortia. And in the end, the companies will have to build most of such a large science infrastructure. And that means that also on that side, there's a lot of people working on this edge between science, research, engineering, development, and really bringing it to an application. And of course, this also happens a lot in industrial technologies. So one thing you can think of is to bring a technology that is developed within a university outside the university. Here you see some examples in Leiden that actually have made it from university research to industrial applications, but also large-scale industrial R&D in the industrial laboratories that also work together with the universities, but on the other side, let's say, on the industrial side, there's a lot of industrial research and development going on. And in this program, we will bring you in contact with that and also learn you the skills that you need to work in such an environment and gain the first experience of how it works in such an environment. To give you an example from my physics background and optics, It's not the same working as as a scientist in an industrial environment. It is not the engineering, building the things, all the technical details that we want to train you in the program, but making this combination between science and the application, applying scientific knowledge, but also the way to develop new knowledge and to do research and to bring that into these engineering and industrial programs. So as one example, for example, for the Einstein telescope, but also other applications, you would like to extremely accurately determine the position of a spot. So you have light coming on the circular aperture, and then you look in the far field, and then you see a pattern, a diffraction pattern. And then the question is, how accurate can I actually measure the position of this spot? Well, in traditional optical engineering, you would say, well, it is a diffraction spot, so it's a diffraction limit. The spot size is limited by diffraction, and the diameter of the first Airy ring, the sine of the angle, is 1.22 times the wavelength over the diameter of the spot, or sorry, of the aperture that the light goes through. So this is what we all call the diffraction limit. So if you want to go below that, well, forget it. This is the limit. And this is where the science comes in. Is this now really the limit? And in what sense is this limit determined? And could you overcome that? Well, one thing that, for example, what you could do one level beyond is if you can calculate very accurately what the pattern should look like, then you can fit to this pattern. And that means that you can much more accurately determine the position of this spot because you put in a priori knowledge on what the instrument is actually doing. And this will give you easily a factor of 100 below the diffraction limit. So the diffraction limit is apparently not the limit. And if you then have even higher requirements, let me see. Next page. If you do this fit, then you will be limited because you measure on the intensity by the linearity of your detector, for example, electronic noise, but also photon shot noise, because this light, of course, in your detector will be detected as individual photons. Now, if you think if this is still not good enough and you would like to do it more accurately, then, for example, you could look in more detail in the structure of these rings, because if you look into the optics of what such an Airy pattern looks like, then actually what you see here in this graph, the red is the intensity, but the blue is the amplitude, is that the amplitude actually changes sign in between these rings. So it means that there's phase flips between the rings, and that actually corresponds to a singularity in the phase in the optical field. And that means, and you already see that in the blue diagram, that you have very steep gradients in the intensity around these dark rings. So you can much more accurately determine the position of the spot by measuring the position of the dark rings than to try and measure the maximum. So if you develop a method that can actually very accurately measure these dark rings, then you would be able to go even much lower than trying to fit the intensity in the peak and in all the rings with a fitting program. So the other advantage, if you look at these dark rings, is that it's not only a steep gradient, but also the field is supposed to be zero there. So it means that you can do a null measurement and you don't have to measure the absolute, but you only have to measure whether there's intensity or not. And that means that you're not sensitive to the sensitivity of your detector. Maybe you could even think of a more simple way to measure the position of this beam, and that's may put in a quadrant detector. I've sketched a little bit what that could look like. You let the beam fall on the cross between 4 segments of a detector, and then you can easily calculate the position by looking at the difference between the intensities in these quadrants divided by the total intensity. And that gives you a position of the beam. And what is nice, if the beam is centered on your quadrant detector, actually these positions become zero because the intensity on the left and the right-hand side and the top and the bottom side are identical. And if you do this, then you can easily go, well, not easily, but if you're a bit careful, you can go a factor of 1,000 below diffraction limit without doing extremely difficult things. So what is the limit if you do this? Is it still diffraction? No, it's not diffraction what is the limit here. So the diffraction limit actually does not apply. It is a bit of the linearity, but if you do the null measurement in the center, you also get rid of that. There's the difference between the detector. There's all kinds of technical problems. There's electronics noise, but there's also one fundamental problem, and that is photon shot noise. And if you do this carefully and you measure, for example, n photons in such a quadrant during the period that you're integrating, this noise will be the square root of n. So Mother Nature allows you, gives you a limit on how accurate you can measure this. And now you could engineer such a system that really reaches this square root of n, and that is what you can do. And the question is, can we even do better than that? And this is a bit the state of the art where we are now. But if you then look at the physics, you say, well, if it's the intensity noise of this n photons, why can't I change the properties of the photons of the field, the statistics, the quantum mechanical statistics of the field? And in physics, you have the Heisenberg uncertainty relation between the intensity and the phase of the field, of the photons that you detect. But in this case, you don't care about the phase so much. It is more the intensity. So you can actually squeeze the light and trade amplitude noise against phase noise. So if you use this much more advanced physics for this instrument, you can get non-Poissonian photon shot noise, and therefore you can get below this square root of n noise. And that means that we have, again, beat the limit of how accurate you can determine the position of this beam. But then you end up with a new challenge, which is really a big challenge that we're facing at the moment for gravitational wave detection, both on the ground and in orbit. And that is that you want to create a high degree of squeezing, so then you have lower noise, but you also want a high intensity because then you have a large n, and that also means that you have lower photon shot noise. So this is the type of challenge where you want to get to the absolute highest performance, really reaching the limits of nature, where science comes in to help the engineering forward, to develop new concepts and to be able to develop completely new technology that can really change, have a big impact on society. And one example is the Einstein telescope, but also, for example, ASML, the lithography machines, the initial first rounds where ASML became important is that they had an extremely accurate way of aligning the wafers to the reticle after when they do subsequent illuminations. And that really, the trick at that time was to be the best one in the world to extremely accurately align these reticles with the wafer. And that is also a positioning problem. And you could even think about using squeezed light in order to go beyond the limit where they are at the moment, although I think that that is not the limit at the moment. So this gives you hopefully a little bit of flavor for what we would try to achieve in this program, how we combine science with a bit of engineering, with a bit of industrial research and the application. So we do not only want to teach you everything about the applications, but it is about this combination, this boundary between the science and the applications where we in this program operate. And therefore, we expect the students to follow the compulsory course in their own topic in the main program, in the master, in the first 3 semesters, and also have to choose some high-tech innovation courses from the own topic. And then there's one overall course or part of the program that we do together with all the students from these 5 different topics. And then part of the research master program is to do an external high-tech innovation research project. And that, of course, should be industrial research, at least related, and could also be in an industrial research setting itself. For this program, from all of these 5 topics, there's a few different lectures that you have to choose a few from, and that are really within the topic of the master itself, but that have a very strong link with this high-tech innovation and industrial application in the program. So a fair part of the education overlaps with the normal program. But these are compulsory topics, at least you have to do a few of those, and this external internship in industry or industry-related topics is what in the specialization you do on top of that. And of course, what it will lead to is that in a lot of the things you do, you will do that with the mindset of how this applies to and how you can use that in a more high-tech innovation and maybe industrial setting. So to conclude, this high-tech innovation specialization program. It is a full master program in the field where you choose to study, and within that it is a specialization. So all of these 5 topics have a high-tech innovation specialization, but there is a bit of overlap. There's also interdisciplinarity between the fields, so we will bring the students of the other fields together, but also in the projects and also in the topics. In some of the courses you will see that people from the other topics in high-tech innovation will follow that as well. We will try to connect, we connect as much as we can with industry practices. One of them is to learn through real-life industrial case studies. So, for example, to in the courses work with those, or the internships that you will do in an industrial setting. Also by inviting people that work in industrial R&D to participate in the education program, and also to give more attention to the way that R&D is performed in an industrial setting. So that means more interdisciplinary, more teamwork, and more also other, let's say, parties that are also doing the building, or that can manufacture things, that use the data in the end. So it is a more, let's say, open way of working with more teamwork, with more disciplines than what you would typically see in a single topic study. And this program is intended to prepare you for a career in industrial R&D. I think it is also very applicable for development of scientific instrumentation. That is not only for science, but also scientific instrumentation that is developed and used in industry. And a bit more generic also for technology-driven engineering and project management in many areas where high-tech systems are being developed and where the mindset of a scientist can really help to boost the innovation. Thank you for your attention.
Questions, anyone? We are more than happy to answer here, and we found in the past that actually those are very good ways to give a little bit more of the background of the program, things that we definitely try to capture in this presentation, but when we are just broadcasting information, we can't always get the nuances right. That's much easier in question and answer. So I very much hope that you have a few, and we're here to answer them for you. Please post any questions in the chat.
To get things started, I have one question for you, Konrad.
Yes.
If you do this industrial internship, does that mean that that is the only one that you're doing, or will you also be doing research projects at the university?
No, the idea is that you get the best of both worlds. So you do 2 research projects. One is a research project here at the university in a mostly academic setting, really geared towards the core of the program that you will follow. So if you do a physics high HTI specialization, you do a physics research project in the physics labs here. If you do a chemistry HTI specialization, you do a chemistry project in the chemistry department here. But then there's a second project, and that's this more HTI oriented project. And the default idea there is that we get everybody in an external setting, in an industrial setting, precisely to focus on the aspects that you just highlighted, that you learn how to apply the knowledge that you've learned in your core program in an industrial setting, which is often in a larger team, but also often crucially in a team with people with different skills and specializations, right? If you do a physics project here or a chemistry project here in a physics or a chemist lab, you will only be talking to physicists or chemists. If you do an industrial R&D project, you often have to talk to a software engineer, to a material scientist, to a chemist, if you're a physicist or a chemist, right? Or an astronomer or someone who has an optics specialization. And so this interdisciplinarity is really a new core thing that you learn in this HDI specialization.
Yeah. Yeah, we have a question. I think that you're also, as education director, are most suited to answer.
So the question is it possible to do a pre-master or do a pre-master somewhere else and then come back to this study? The very quick answer to this is yes. But the simpler answer is that there are essentially 5 fields, and you always start in your core, your main program. So the pre-master question is more related to that core program than to the HTI specialization itself. Because within the HTI specialization, once you are in, right, then we try by this broadening profile of the courses, deliver you not as a pre-master, but integral in the master, the necessary knowledge to be able to do these skills with your fellow HTI students in the other main programs.
Yeah, and I think that also answers the question whether this course is accessible with just a bachelor degree or not. The answer is yes. So you need to have a bachelor that is applicable to the main topic that you want to do. But that is enough. So it means that this high-tech innovation specialization will be part of the master that you get access to with your bachelor. So you do not have to do any step after your bachelor before you can go into this program, but you have to choose the major subject. And then within that subject, you can immediately choose for this specialization. So then from the start, we will incorporate more of the HTI part in the normal program.
Yes, that's correct. Okay. The next question is, do you have to apply at the company completely on your own, or is there a list of companies you can apply? So one of the things that we are doing as the university is we are actually establishing all contacts. We have already established quite a few contacts with various companies, not just here, but actually also in various other parts of the Netherlands, although the main focus is around Leiden and the region, precisely with this idea. Do you have a space or an option, or can you help us teach students in this HTI specialization? And of course, it's also in these companies' own interest to find students who are interested in what they do and create people who are well educated who can then later apply in the company. So in principle, that responsibility to find positions in companies is ours. And the idea is that there's a sort of a small marketplace, right? That you, when you get to the stage that you do this research project, you have several of these projects ideally to choose from. We will do our best. We cannot promise anything. This is always a little bit of give and take, but that is the fundamental driving idea.
Yeah, and there's another thing that many of these very scientific programs are done in collaboration between different parties anyway, with industry and universities or with institutes. Of course, it is nice to work in a company, but it is also very interesting to work in a collaboration with a company. And that could mean that you're not full-time working inside the company, but that you're working on a program together with the company. And so I think there will be, depending on your interest, there will be different scenarios, and we will help everybody with finding a position that is at least has a sufficiently industrial character, that it is sufficient for this high-tech innovation. If you have an idea, I would really like to work in this type of company, then we have to see, maybe we have already an agreement for internship positions, or maybe we can arrange that, or maybe you can arrange it yourself.
Next question is, the astronomy master also has the master instrumentation. Is there somewhat of a similarity with this master or not? The answer is indeed, there is somewhat of a similarity and overlap with the astronomy master, although the astronomy master instrumentation is very much geared towards instrumentation and optics, built for, let's call it, academic scientific discovery. Okay, there's of course an overlap here with high tech, especially cutting edge industrial application of optics on its own. And so indeed, then it's a little bit up to you which direction you want to go. But the focus of the high-tech instrumentation is also cutting edge fundamental science, but then with a goal of applying it in an industrial research setting rather than an academic research setting. And so there are some differences at that aspect. Sort of at the most core, if you talk to an astronomy master in instrumentation, you will mostly talking to optics and astronomers. Whereas what we try to say is that once you go to industry, and high-tech innovation, you often have larger teams. You have to take this a little bit with a grain of salt. This was a very sort of broad generalization. If you do the large sort of big astronomy projects, such as a James Webb telescope, you are also working in super large teams. And so there is a similarity, right? But there's a nuance in the different sort of what the end goal of the program is.
Yeah, and if I may add something to that, there's different roles also in the large-scale astronomy instrumentation. And what we will try in this program to get you more acquainted with the way that industrial R&D is done. So you're talking about program management, about milestones, about development funnels, about industrial intellectual property rights. So we, in this program, try to give you more, to learn more and get more skills and knowledge on the way that this is done on the industrial side. To give an example, I come from academia, then I worked for 20 years on the industrial side in the space sector. And then you really see that these are two different ways of looking at the same problem and also very different ways of working. And I really strongly believe that the combination of the two is where the most value is. So if in an academic setting you're able to see both sides, if you end up in such a direction, then you already know both sides. And that is a bit different than the instrumentation master. And so I think they already do part of that, but we really try to bring you as much as we can in contact with the way that this is done on the industrial side.
Any further questions?
I have one question. If you do this in industrial internship, is that then going to be, let's say you just are there and you are working with them and you do some things for them and that is not disclosed and it's not really research, but more like a practical internship? Or are these internships also supposed to be a research development project and also with a university supervisor, second supervisor maybe?
That's a very good question. Yeah, so at the end of the day, that research project, even though you do it externally at an industrial partner or a research institute partner, that's not the university itself, it's still part of your master's education. So it still is, there's still a teaching aspect and knowledge transfer aspect to it important. And we also have to evaluate that and give you your degree based on that. So there's absolutely also always a university supervisor involved. Issues with non-disclosure, that is always tricky, but even that within certain reason is possible. So you can even still work in certain cutting edge sort of proprietary aspects within a company, given some leeway, because especially the university supervisor and the board of examiners have to be able to give you a grade on this, right? So but these are aspects that we have considered in detail, and so we try to sort of move in this transitioning way, actually in a way that Marco said, right? It's precisely on this interface between the academic world and industrial world, and in this particular case, it's the interface between the educational aspect of your master and already having a job in a company. So there are certain aspects that are still education-like. You have to give in a certain way, be able to give a presentation about it, where you can show what you have learned. It has to be at a certain level that is corresponding to people who don't follow this program, but stay in pure physics or pure astronomy, right? So that we can give you a grade at this level. But the idea is really that you sort of transition also towards the experience of how science is applied at the frontier in an industrial design setting.
Yeah. What if I can add? I think what I see is that in all the topics within the science department that are part of this program, there's already a lot of this type of collaborations, and there's a lot of experience with making sure that the internship or the project that you're doing externally, that is really of an academic level and is of an academic nature, and that the results that you have, that part of that will be public, and that is done together with the university can be shared. And maybe it could be that a little bit of the thesis that you write, that a few pages are left out in the final publication. But I think that is the level. So the idea is not to go there and work for them for 3 months and then everything is dead and silent. So we also want the students that participate in this specialization, bring them together a few times also to exchange experiences of what do you learn outside? What does that mean for me? What can I learn from the experience of others? Because everybody will be in a very different environment. And I think the interaction between that is also very interesting to see what the difference is. For example, if you would work at the European Space Agency, at ASML, at Philips, at a small technology startup, these are all very different.
So let me also then jump into some of the core aspect that Marco just touched about this external research project. It is a research project. It is going to be your project. It is not spending 4 months in a company and doing their work, right? Bringing the coffee to the director, for instance. I mean, to put it bluntly, no. The point is really, you have to be able to show that you learned something new, right? You don't really have to break scientific new ground and win the Nobel Prize, right? But there should be an absolute learning component for you, and that's a key part. And the best way that we have, as Marco said, we have quite a few years of experiences in all the various fields, is that this is a direction where the company itself also wants to learn, right?
And I think the Nobel Prize would not be excluded, would still be possible in this setting. Any other questions?
Any further questions? Shoot, on all aspects, all regards.
Perhaps
Okay.
Perhaps we can wait 2 more minutes till it's 5 past.
Yeah.
And then we wrap up the session.
Yes. And if you have any questions that come up later that you realize that, you can always contact us. The webpage with all our contact information is up and running. You can write to me. I'm the education coordinator. I try to coordinate everything. And Marco is really our primary proponent. As I said, he's going to teach this special course that overlaps everything. And from his background, he's also the one with the most experience in both fields. So you can write either one of us with any questions you may have, such as these questions. Don't hesitate to do that. We're more than happy to answer them. We are, as a University of Leiden, extremely excited about this program and the opportunities that it gives us. So we hope that you are just as excited as us and come join us starting next fall. And with that, if there are no further questions, I think we can end the session. And I look forward to hearing or seeing you soon.